right, hello Emma and Rachel and Marcus. This
Marcus,
is 5-6.
You smell funny.
Emma, I'm mad at you. You took my
Whatever.
card.
Anyway, 5-6. Summary of curve sketching. So, like when we're graphing stuff, or graphing functions, like you can, graph a normal thing by either plotting points or plugging it into your calculator or doing those things. But like we know, like from the way that math works, that like first derivative, second derivative, those things can tell me things about a function, okay? So we're just talking like characteristics of a function, that type of thing, okay? Here are some things that we could analyze on a graph. Like this is what we've been learning like all throughout algebra 2, algebra 1, whatever, like all the way through, okay? Some of these a graph is not going to have. Like not every graph has a vertical asymptote. Not every graph has a horizontal asymptote. Not every graph
has an X or Y intercept.
Has an X or Y intercept, right? So like there's that thing, okay? So let's go through these guys and let's figure out, I'm gonna write some stuff on the left and the right and we can just discuss like how we find each one of these things. So how do you find like X intercepts and Y intercepts?
Plug in for the opposite.
Yeah, plug 0 in for the opposite. So like, yeah, you're all saying the same thing. So plug 0 in for the opposite variable, I'll say. So if you're trying to find the X intercepts, you plug 0 in for Y, Y intercepts, plug 0 in for X. And that's how you find those guys, okay? All right, symmetry. I'm gonna put him over here to this side, okay? There are 3 different types of symmetry. There is X-axis symmetry, there is Y-axis symmetry, and there is origin symmetry, okay? Like X-axis means like it's reflected across the X-axis, so it might look something like this, like a parabola like that. The Y-axis symmetry would be the same, but like across the Y. And origin symmetry, the one that I think about, is like X to the 3rd power, something like that. You don't necessarily have to graph those, but how do we test for symmetry? Do you remember?
You change the signs.
You change the signs. So like X, if I'm going to test for X-axis symmetry, I plug what?
Negative Y.
Negative in for Y, and I see if it switches back to the original function, right? For Y-axis symmetry, I plug negative in for X. See if it switches back. Origin symmetry, I plug a negative in for both of them, and I see if it switches back to the original function. Got it? Okay, domain and range. We're going to specifically talk about domain here, but there's two main things that screw up domain. I'm going to talk about the domain errors because those are really what we are kind of looking for. Number 1, number 2. Number 1, we never want to have what?
Square root.
A negative inside a square root. Sure, that's one of them. And we never want to divide by 0. Okay, those are 2 things. Now, in addition to that, if you're dealing with story problems, we can only have like positive lengths and positive distance and stuff like that. So sometimes your domain can be restricted if you have a story problem. But there's that. Okay? Continuity.
That is not how I read.
Things that screw up continuity. What like makes a function not continuous?
Pause. Pause.
Okay? Vase. So vase and what else? Holes and piecewise, I heard Sarah say. Piecewise functions. These are all things that can cause discontinuity.
Wait, why is it ha in a ha?
Why not a
A
ha?
ha doesn't cause a discontinuity.
Why?
Why not?
Because when you're talking about continuous functions, you're talking about the x coordinate. So like a ha, right here, like let's, don't draw this, but let's say like this is a ha, right? Okay? And you have a function that's like, let's say it's just an exponential function. So he's doing this, right? that has a domain, all reals, right? He's not gonna like derail at any point, even though he has a ha. But if he has a va, so like let's say he has a va at 1 right here, and he has like this function and this function, I'm going along my function, I'm gonna derail at that point, right? Like here, I can set my train here and he's gonna be fine all the way through. Does that make sense?
Yep.
So, ha's don't cause discontinuities.
Technically, it's still going on forever.
What?
The number gets smaller and smaller and smaller.
What you talking about?
Like going to the va.
Oh, for a va?
Yeah.
But I can't jump from one side to the other side.
Why?
Because, so like this guy, like if he's doing this, right? Like if I put my train here and I go along, like I can't cover all of the x's to jump from this side to this side without my train derailing. Does that make sense? I have to be able to cover all the x's without the train derailing. Okay, so that's how that works. Continuity is like based upon like your x values or your domain values. Okay, vertical asymptotes. How do you find vertical asymptotes?
Set it equal to.
No.
Set what equal to 0?
The bottom.
The denominator. Set denominator equal to 0, and that's how you find your vase. If he doesn't have a denominator, he has no vase. Okay? Differentiability kind of goes with continuous functions. So we want to make sure that he doesn't have any of these, but also that he has no cuspids. I think I spelled that right. No cuspids. Okay, so he doesn't have any sharp tippity tips, right? For differentiability. So he can't have any vase, holes, piecewise functions where it causes discontinuity, but also no tippity tips for differentiability. Okay, and if he has none of those things, then you don't have to worry about it. Okay, relative extrema. We're going to talk about this guy. Relative extrema and points of inflection. Those are kind of related. How do you find relative extrema are maxes and mins? How do you find the maxes and mins?
First derivative.
First deriv. Okay, here's the first derivative, and you usually set that equal to 0, and then you find increasing, decreasing. Right, like we do that whole set, increasing, decreasing, etc. Okay. Concavity. Were we talking about concave up and concave down?
Second derivative.
Yep. Concave up, concave down. We do the second derivative. Second derivative equal to 0. And then points of inflection are where he changes concavity. Okay, so all those things are kind of related to what we just did in like the last couple sections. Okay, he changes concavity there. Okay, horizontal asymptotes and limits at infinity. I'm going to talk about both of those together because they kind of are like they're related. Horizontal asymptotes are infinite limits, and those can like be used to determine what a graph looks like as well. Okay, so for Haas, I don't know if you want to write these rules down, but if n is less than m, if n is equal to m, if n is greater than m, okay, y equals 0, y equals LC over LC, and then this one is none.
When you write
It's top heavy.
y equals 0, you can't just put 0, right?
If they're talking about the limit, if they're saying what is the limit, you would just put 0. But if they're saying what is the horizontal asymptote, you're going to want to put y equals 0 because it's an equation. Does that make sense? So if they're saying limit, what's the limit? You would just put 0.
It makes sense.
If they're
but
saying
I'll
what's the
remember that.
y equals 0. Okay, got it? So all of those things, like we've been studying x and y intercepts since we were in algebra 2, or probably in algebra 1, right? We've been talking about some of those things all the way through, just recently adding like basically these ones to our differentiability.
Really
I guess
different.
like mainly these ones is what we've talked about a lot in Calc. Okay, all right, let's go down. This is the only thing that we have to do. Like you have one function, and we're gonna try to like write down all of the things that apply. Okay, now I know that some of these I can cancel off, right? And this is what you're gonna do on your homework assignment. I have a little chart right here for you that's gonna help us like differentiate our stuff, so like have everything nice and organized. Okay, and I strongly encourage you to do a kind of a chart like this. Do I have a chart ready to go for you on the homework assignment? Yeah, on the homework I don't give you a chart. Yeah, I do kind of. No, I don't. No, I don't. So you can make a chart. I don't care, however you want to do this. I think the chart helps. But anyway, this is the function that we're dealing with. Okay, so let's talk about things that we can like debunk or get rid of. What?
There's no y-intercept.
There's no y-intercept. There has to be a y-intercept.
No, there's not.
It has to cross y somewhere.
It has to cross y somewhere.
Is it up there?
What? He has a y-intercept.
Where?
Where's the intercept in the y?
It's 0. Are you stupid?
That's 0, you silly boy. Isn't he crossing the y at 0? You can see it on the graph.
for the
You silly boy.
Excuse me.
The x-intercepts are really ugly, okay? So, okay, let's go ahead and do that. If we're doing y-intercepts, we plug 0 in for x, right? X equals 0. If I plug 0 in for x, I have 0, minus 12 times 0, plus 48 times 0, minus 64 times 0. And that's going to end up being 0, right? My y-intercept will be 0. So, he has one y-intercept, which is 0. Do you have more than one y-intercept?
No.
Yes.
Because if you do, then it's not a function.
If you do, then it's not a function. So you could have
Silly.
something that looks like this,
You
right?
still
Where
have
it's 2
more than one.
y-intercepts,
Stupid.
but then
It's
that's
not
not
a
a function anymore.
So?
So,
It's not a function.
if you're talking about a legit
Yeah,
function, he will never
Yeah.
have more than
Because
one
it's my
y-intercept.
imagination.
Okay?
Me too.
x-intercepts. How many x-intercepts can you have? Shh. How many x-intercepts can you have?
As many as you want.
As many as you want. He can
This
cross
one
as
can
many
have
times as he wants
4.
to, up and down, whatever, I don't care. Okay, this one has up to 4, right? You said? Okay, now, plugging 0 in for y, we have this thing going on. Oh my goodness.
I'm gonna do this in my calculator.
Pull something out.
Pull something out.
X to the third. X.
We could pull an x out front, right? Don't write this down anymore, because we're gonna stop. Like, I'm not gonna actually do this one. 12x squared plus 48x minus 64. Okay, we pull an x out. So yeah, that's my strategy, is do like a factor by grouping thing. So the deal here is, if we could pull an x squared out, we would be left with x minus 12, right? This one we would have to pull out, I don't know, like 8.
4. Yeah.
We pull out an 8. 8, and left would be 6x minus 8. No, we could pull out a 16, actually. If we pull at 16, we would be left with 3x minus 4, right? But the problem with that is, x minus 12 and 3x minus 4 are not the same. So we couldn't do that. So, do you know what we would have to do? We're not going to do it, but you know what we would have to do finding the x-intercepts?
I don't. Is 4.
Quadratic.
It equals
No,
4.
because it's not a quadratic.
4.
How do you find the x-intercepts when nothing else works? Like, you can't factor by grouping.
Graph it.
You can't do
No.
whatever, like, graph
A
it.
quadratic.
But he's not a quadratic. He's x to the 4th power.
Your P's and Q's.
Your P's and Q's. P over Q, and then you list them out and you find which ones plug in and work, right?
No.
We're not gonna do that. We're not gonna do that.
I don't
okay?
remember how to do that, but I remember that sucks.
So, what we're gonna put here
I
for
really don't know how to
x-intercepts,
do that.
okay? We're gonna put P over Q method, and we're gonna pretend that we did it, and we're gonna say equals ugly, because I don't wanna do it, okay? If it's too ugly and it's not worth my time, let's just skip over it, right? So he will have some x-intercepts, up to 4, right? But they're really ugly, so we're gonna skip them, okay? Alright? Okay, now, let's talk about some of these other things. What will he not have?
That work?
Domain error.
He won't have any domain errors, okay? So, for domain, what will the domain be then?
All real.
All reals, okay. What about any of these other things? Any of those other things we can skip over?
No ha, no va.
You will have no ha, no va. Boop, boop, so none. None and none. Let's talk about end behavior. How do you figure out what, we didn't talk about end behavior up above. This is x to the 4th power. That's his parent function, right? Like x to the 4th. What x to the 4th is gonna go?
Coming from infinity.
Up and up. So whatever he looks like in the middle, we don't care. We don't care what's happening here, but end behavior, he's gonna go up and up. So, you could say as x goes to infinity, the y's are gonna go to infinity. And as x goes to negative infinity, the y's are gonna go to infinity as well. So he's going up and up. That's what he'll look like. Okay? Alright, now let's do our derivative stuff. Okay? Let's do all of our derivative stuff. Okay, let's do first derivative. Alright, I'm gonna do them over here. First derivative.
4x to the 3rd minus
Okay.
36x squared plus 100 or 96x minus 64.
Got it. Okay, that's your first derivative. If you're running out of room and you want to put some of these on the back side or whatever of this sheet, this is like the only sheet that you have, or down here, wherever you want to put them, okay? That's your first derivative. Okay, let's set him equal to 0 real quick. So your first derivative, if you want to rewrite him over here so you have everything together, that's fine. 36x squared plus 96x minus 64. So you want to do that, there it is, okay? All right, we want to set him equal to 0.
Pull out 4x squared.
Pull up 4x
No, you can't. You can't.
squared. What are you doing?
No.
You can't. You can't. Yes, you can. You can't.
You can pull up
You can pull out a
4.
4.
First two.
Is this
Pull
where
out
I
a
need
4.
to find the max and mins now?
Yes, yes, yes. So we're setting him equal to 0 to find the maxes and mins. Exactly.
Hey,
What would you like to do first? You want to divide? We can divide everything by 4. Divide by 4. Divide by 4. Divide by 4. Divide by 4. Right? And divide by 4. And we can like, since we're not dividing an x off, we can just throw the 4 in the trash, right?
Yeah.
X to the 3rd minus 9x squared plus, that would be 24x. Can you do that in your head?
Nope.
Yeah.
96 divided by 4. 9 divided by 4 is 2 with 16 left over.
16.
24. Okay. Minus, this one is 16 equals 0. I don't think you can factor by grouping that. Actually,
2 and the last 2 together?
No.
Why not?
Well, because
Oh,
if
yeah,
I
you
group
want
these two, and I pull an x squared out, I'm left with x minus 9, right? Am I gonna get x minus 9 if I pull anything out of there?
Maybe.
Not
I don't
going
know about
to
that.
happen.
So we have to P and Q.
So, do we have to P and Q this?
Maybe not. This is a bad one.
You
Ugh.
made this thing, Griffin.
Did you make this?
Do we have to P and Q any of these?
No,
You
I don't think so.
Well, I already
Can we
know
just do
that.
number 1 number?
What?
We just do number 1 number?
No, 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 no,
It's a
no.
lot nicer.
No, 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 no. Well, then you can do it by yourself.
I'm not learning anything.
P's and
from
Q's.
this
Let's
stupid
see. 3 of them have to be a thing. I already have the answer right here. X is 1, X is 2, X is 4. But I don't know which one's from the first derivative. Let's do the second derivative. Let's do the second derivative and we'll come back to the first derivative.
Well,
What's the second derivative?
12x squared minus.
No. 3x squared
You can
minus 18x.
you can derivativate this one.
3x squared minus 18x plus 24. Pull out.
Plus 24
Race.
equals 0. Okay, we'll do this one and then we'll come back to the first derivative and see what we get. Okay, if we divide by 3, can we divide by 3?
Yeah.
We get x squared minus 6x plus 8 equals 0. That one's nice. Okay. Alright, I'm gonna write that down for my
Negative
second
2, negative
derivative.
4. Boom.
X squared
Ah, shoot. I
X equals
screwed
2
up.
and 4.
minus 6x plus 8. Oh, actually, I should put, well, it doesn't matter. It doesn't matter. Whatever. Okay.
You're right.
X squared minus 6x plus 8. Got it. Okay. You can do what? 2 bubbles. Multiply to get 8, add to get negative 6.
Negative 2, negative 4.
Negative 2, negative 4.
So 2 and 4 are your critical numbers.
So x equals 2 and x equals 4. Okay. I'm going to list those two guys down here for critical numbers. We know that 2 is a possible critical number and 4 is a possible critical number. Or they are critical numbers. They're possible points of inflection. Okay? So 2 and 4, because they came from the second derivative, they are possible POIs, right? Maybe they're not POIs, but they're possible POIs, right? We have to test to see. Okay?
You guys know if it's not a POI.
If it's concave up and then concave up again, then it's not a POI. If it's concave up, concave down, if it switches concavity, that's where it's a POI.
And you plug POIs into the original.
To find the y coordinate for that POI, yes.
Okay.
Okay, alright, so we've got those. They also say on here, because I'm looking at my table, that x equals 1 is a critical number. Where did that one come from?
From the first derivative.
Probably from the first derivative. Should we cheat and say that's
Cheating
my
is not
other
a
one?
Very good thing. to
Should we
do.
cheat that one and see?
Yeah.
Okay, so 1.
Sure.
1 is a critical number from the first derivative. He is a what? He's not a possible POI. What is he?
Max min.
He's a possible max or min. And we have to figure out which one he is. So that's a possible POI, that's a possible POI, that's a possible max min.
We do not have to figure out which one it is.
But we're gonna. Okay, because we have
It's
three.
gonna be a minimum because we already. Alright, no, you can't say
Because we have 3 critical numbers. 1, 2, 3. This is from the second derivative, this is from the second derivative, this is from the first derivative. Okay? Because we have 3 critical numbers, we have 4 test intervals, okay? Remember before how we did the table and we did the test intervals across the top and then we did like the derivative stuff here? It's reversed for this table because we have lots of things to do for each one of these intervals. So I kind of reverse the table. You do however you want, okay? So let's do this. X equals 1 is my place right here. And what I've done here is I've said f of x, meaning we're plugging that number into the original function. And I've left a column there to do that just so I can find those like physical coordinates, right? We are not going to fill this box in, this box in, this box in, this box in, right? Like we're not going to do those boxes, okay? Because I only want to plug those actual points into the original equation. Does that make sense? To find the y coordinate. So this is the coordinate 1 comma something, 2 comma something, 4 comma something. And if I plug those in to the original function, cheat from the graph and tell me what you get. 1 is at
Negative 27.
negative 27. You're so brilliant. 2 is at
Negative 16.
negative 16. 4 is at
0.
0. Okay, great. We plugged him into the original, that's what we get, right? So that's why I gave you this column, was this is the original function. Original. And we're plugging those actual points into the original. Now, the first derivative, okay, this is the first derivative. Okay, we're gonna plug in numbers from these or from like those test points, okay? So which number would you like to plug in here?
2 or negative.
Give me a number between negative infinity and 1.
0.
0. Let's plug in 0. I'm going to put 0 in this coordinate here, right there. And I'm going to put 0 in there because we're going to plug them into the first derivative and the second derivative. Okay? A number between 1 and 2. 1.5. Okay?
Actually, can
A number between 2 and 4.
6, 7, 9.
3.
I don't care. 3. And a number between 4 and infinity. Let's plug in
6.
5.
6.
5. Silly. Goober.
Silly kid. All right, ready? Here we go. So 0. If I plug 0 into the first derivative, this was my first derivative, right? After we broke him down or did whatever. If I plug 0 in there, what are you gonna get?
0, 0.
Wait. Negative 16.
Negative 16. So he's gonna be negative here.
Such a genius.
Okay? He's gonna be negative. Okay.
0.
Now, if the first derivative is negative, that tells me that that interval is doing what?
Down. Decreasing.
Decreasing. So I'm decreasing on that interval. Okay? Now, if we plug 0 into the second derivative, which is this guy right here, okay, what do you get there?
Up.
This is my second derivative. If I plug 0 in, I get 24, right? So that's positive. So it's decreasing. This tells me he's decreasing. This positive tells me he is concave up. Those are my characteristics of that thing. So that interval is decreasing. It's going down, but it's caving upward. Got it? That is the interval from negative infinity to 1. I'm going to show you what that interval looks like. Negative infinity is all the way over here to 1. Okay? So in between these two right here, in that little chunk, is that function going down but caving upward?
So I have
Like right here. Is this going down but caving up? Yeah. Okay? All right. Now let's go on to 1.5. What?
So for the first derivative, when you plug in 0, you don't care what the number is, just the sign.
No. I do not care what these numbers are at all.
Okay.
You
So
don't care?
that makes it nicer because then I don't have to spend all the time plugging crap in and getting an exact value. I just know if he's positive, he's, you know, whatever. If he's negative, he's whatever. Okay, now this is where it's a little hairy. 1.5 is what we're plugging in. So we're plugging 1.5 in there and we're plugging 1.5 in there. Yeah, sweeto.
Why did you make this so
I don't know. Somebody had these in their calculator.
No.
Want to plug them in? Or want to give me a calculator and I'll plug them in?
I'll give you a calculator.
Okay, sure.
There you go.
Okay. Am I doing one of these already? What do you have going on here? Oh my heaven's sakes. Okay.
Let's see.
Okay, now you're fine. 1.5 to the third power
Yeah, have fun with that.
I got a positive.
minus 9. What? You got what?
Positive.
Positive for that one? Minus 9 times 1.5 squared plus 24
Oh, I didn't square my thing.
minus 16.
You go.
Okay, I got positive. I got 3.125, so I got positive. All right, write that down. Positive.
So.
Okay.
So you're not doing
If I plug 1.5 into my second derivative, 3 times 1.5 squared minus 18 times 1.5. Is that plus 24? I can't see.
That's a good
Plus 24? Okay,
Not
that
bad.
is 3.75, so also positive. So, what's he doing in the second interval that we have?
Increasing.
Increasing, but he's still concave up.
No
Okay,
kilowatt.
now, real quick.
Everything because of the
This tells me right here, okay? Are you guys listening?
Yeah.
This tells me that on one side he's decreasing, meaning he's going down, and on the other side he's increasing, which means he's going up. Okay?
He has a
So
min.
he is a min. Okay? Now, is he a POI?
No.
No, usually if he's a min, then he's not a POI, right? So this is a minimum point because he's switching here, but he's not switching here, so he's not a POI. Got
Hey,
it?
whoa.
Whoa, 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 whoa.
You said normally if he's a min, he's not a POI. Is there a
Never,
chance?
never. I mean, always if he's a min, he's not a POI.
Okay.
It has to be one or the other.
Got it.
Okay? Got it?
Uh,
Yes. Okay.
Oh, my jar.
3, if we plug 3 in. Let me go back up to my function. I'm gonna type in 3. 3. 3. And 3. Okay, I got 2, which is plus. Let me keep everything the same color. Plus. Okay, if I plug 3 into the second one, I get, un momento por favor, 3.
Plus. It'll be plus.
You think it's gonna be plus?
It's gotta be plus.
It's gotta be plus.
Are you looking at the graph?
Yeah.
No.
It's gotta be minus.
Dang it.
What? It's a possible POI, so it would only make sense to be, you know, switching concavity if it's a POI.
What?
You guys are silly. Okay, what's happening here? What does this mean? He's increasing, but he is concave
CD.
down, right? He's concave down. So he is not a max or a min, this tells me that, okay? But he is switching concave up to concave down. So he is a POI.
What's your pain in the ass?
Got it?
I'm good for it.
Okay, next, if I plug in, what, oh, we're plugging 5 in for this next one? Okay, 5, and 5, and 5, and I get 4, which is plus.
Positive.
Okay, and now the last one, if I plug in
Concave up.
5, and I plug in 5, it is plus. So he is increasing and concave up, which means this point right here is a
Point inflected.
POI. All right. One more thing really quick. Okay, so we've got all that stuff figured out. We've got all of it consolidated in a table. One more thing. We had something called the second derivative test. The second deriv test, which said that possible maxes and mins. Which one was my possible max and min? 1. If I plug that into the second derivative, it will tell me whether it's a max or a min, and I don't have to do the increasing, decreasing crap, right? So if I take 1, and I plug 1 into my second derivative, I'm going to do that real quick. 1 into the second derivative
3 minus 18 plus 24.
is 9, which is plus. So if I plug that 1 into the second derivative, I get plus, which means he is a, you remember? Minimum, right? That was like the opposite. So plus meant min, minus meant max, right? Okay. 0 meant he was a POI. So if I were to plug these numbers in to the second derivative, I would get 0 because they are neither maxes or mins, they are POIs, right? That's what that second derivative test told me. Got it? Yeah, look at that. Look at all that mess, okay?
So,
Yes, sir.
so technically,
Mhm. Yes.
you didn't have to plug like 5 and 3 in to find the increasing and like CD and C up, right? We could have just put in 0, or we could have just done the second derivative and seen what it was.
What you mean?
Yeah.
Like, are you saying you knew these were already POIs, so you could have just assumed that they were going to switch?
No, like you could plug in, like you could do the second derivative test, and if it is a POI, like if it is 0, then you know that it's going from C, D, or C up to the other.
Right.
You killed my
Correct.
pawn?
Correct. Yeah. I get what you're saying. I'm picking up what you're throwing down. Yeah, so like we plugged in, we got 0 here. We knew this was already a POI. We knew this is already a POI, right? So then you would have just had to know, like, if this was concave up, this one would have had to have been concave down and then concave up again.
Yeah.
Right. Yeah. I agree. I get it. That makes sense. If you can like get all that figured out in your brain, go for it. Yeah, I totally get it. Yes, that is true. Okay, happy with that? Look at all that mess. Wow. Okay. All right, let's go to the thing.
Mine says ugly, so.
Does anybody know for sure that they want to use the chart? Because I can help you get your chart set up.
I do.
Yeah.
You have a ruler? This has to be like,
Oh, and this is yucky.
Where'd they go? Give me one.
Can we have a little help getting started?
And this one, the back side is going to be nice. I said skip these are ugly for number 5. So x-intercepts, don't find your x-intercepts. The back side is going to be nice because this guy is not going to have what? Vas or has or any domain errors, okay? This one, not so nice because he's going to have a va and a ha and he's going to have like the quotient rule.
No.
No.
We do this one together.
We're gonna do this one together. At least to begin with for the first part of it. Okay, so let's label some stuffs. X-intercepts. Oh boy. X-intercept, that means I plug 0 in for Y. So if I put 0 here, okay, what are you gonna do first?
Add the 3.
Add the 3. So I've got 3 equals 1 over X minus 2. Then what? Multiply by X minus 2. So I've got 3X minus 6 equals 1. Okay, then what?
What? Wait, what?
Or multiply by X minus 2.
Add the 6.
Okay, let's add the 6 over. Plus 6 plus 6. So I've got 3x equals 7. And my x-intercept's going to be 7 over 3, or 1.6 repeating. So 7 over 3, which is 2.3 repeating. I can't math. 2.3 repeating. Okay, so I have an x-intercept at 2.3 repeating. I'm going to put him like right there. Okay, put him as a little dot. The y-intercept, this one's easier-ish, probably. Plug 0 in for x. So I've got...
Graph it, and then we can
No.
make the graph.
Did you mathematically get that?
Yes.
3.5.
That's too bad.
Negative 3.5, right?
3.5.
Okay, because this is negative 1/2. So negative 3.5. Those are the only x and y intercepts. Negative 3.5 is right there. That's where he's touching. Boom. Okay. All right, let's talk about some other stuff. Besides increasing, decreasing, max, min, concave up, concave down, points of inflection. What about vertical and horizontal asymptotes?
Yeah.
Oh yeah.
Okay. He will have a vertical asymptote at where? At 2. If you set this guy equal to 0, and you add the 2 over, x equals 2. That's my vertical asymptote. Let's graph him. X equals 2. At 2 on the x, it is right here. That's my vertical one. X-intercept is 2. Okay? Or the vertical asymptote is 2. Okay? For ha's, let's talk about n and m. N equals m equals...
Kyle, I dare you.
Oh, wait a minute.
There is
Wait a minute. Wait a minute.
It's 0 over 1.
Okay? We gotta look at the ha for this, and we gotta look at the ha for this. Like the two pieces, right?
The heck?
So what's the ha for this guy?
2.
0 over 1.
Okay, he'd be 0 over 1. And so what is the ha if
0.
Y equals 0.
y equals 0, okay? What's the ha here if it's negative 3? Or what's the limit at negative 3?
Negative 3.
Negative 3. So what's 0 minus 3?
Minus 3.
Minus 3 is going to be your ha. You see how that works? Like you're looking at the limit of each one individually, right? Like the limit of negative 3 is negative 3. The limit of this guy is 0, right? 0 minus 3. So negative 3 is going to be, or really, I'm going to erase that. Really, y equals negative 3 is your ha. Got it? Negative 3. Boop, 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 boop.
So
That guy right there. I'm thinking he's going to be a little boomerangy thing. You thinking what I'm thinking?
I've been thinking.
You think like the boomerangy thing like this, right?
No.
No? He's got to be in those two quadrants, right? Because he's got to have that.
Why does he have to be in those two?
It's gonna be
Because
the other
this dot is right here and this dot is right here.
How do you know you're not wrong?
No, I know my dot's not wrong. All right, let's do some derivatives. I'll do this one. What's the derivative of negative 3?
Negative
Ah.
3.
He's gone. Nah. Okay, next. All right, quotient rule for the first,
Oh, God,
for the first derivative. Oh, come on. The quotient rule's not that bad.
0.
Go to the top and make it a product.
Wait, so the first one's 0.
You could do the chain rule if you want to move him to the top.
Yeah, let's do chain.
Hodgson, no! The chain rules.
Better than
Duh.
stupid.
Whatever.
No, it's not.
Whatever. F prime G minus G prime F. What's F prime?
Parts that is.
0.
0 times whatever G is. We don't even really care because it's going to be 0. Minus G prime is 1 times F, which is 1. Hey, look at that. 0 times x minus 2 goes away, and so your top number is negative 1 over x minus 2 squared.
This is bad.
Boom. Okay, let's go ahead and set that equal to 0.
multiply over. So negative 1 equals 0.
Right. If you multiply the other side to the other side, you get negative 1 equals 0. So what's that mean?
Undefined.
We have no critical numbers from the first derivative. Except,
Could be a,
do we have a va?
You have your
yes,
We have a va at
2.
2. So we do have a critical number. One of our critical numbers is 2. Do we have to list critical numbers? No. So in our like group of critical numbers, we have our va is 2. Like we have 2 as a critical number. Okay, got it? Alright. We're working hard. We really are. We're working hard. Be quiet.
Without us?
We're working hard without you. Okay, let's do
Yes.
the second derivative. Okay, let's do second derivative. Here we go. I'm gonna do what Jake wanted to do. Okay, this is my first derivative.
I'm very
Do
Okay.
not do the derivative thing.
Okay, you guys gotta be quiet. Shut up.
Marcus, yeah.
We're in the middle of a problem. Be quiet. We're gonna run out of time if you
Is
don't
this
be
the
quiet.
last one?
Yes.
Oh,
Okay.
good. We've been doing too much math.
Cool. Okay, there's my first derivative. Second derivative, here's what I'm going to do. Rather than doing the quotient rule, I'm going to move this guy to the top. So this is going to become negative 1, or just negative, x minus 2 to the negative second power if I move him to the top, right? Okay, that make sense? Like if we move him to the top, that's what he'll look like, okay? Now I'm going to derivative him, which means he's the chain rule, right? So the negative 2 comes down in front, which makes it positive 2. X minus 2 to the negative third power, right? But then we have to take the derivative of the inside. What's the derivative of the inside? 1. Okay? Alright, so here's the deal. When we fix him, x minus 2 to the third has to go back down to the bottom. And what's on the top? 2. 2 times 1, right? Okay? That's my second derivative. Got it? That makes it a lot nicer. Let's set him equal to 0. What happens? Yeah, we have 2 equals 0. Like we multiply this stuff to the other side and it goes away. So we have no critical numbers from the second derivative. What the heck? We don't have any critical numbers except for x equals 2, which is my va. So I literally have like nothing happening going on here. What the heck? Okay? Alright. Here we go. Let's do a table here. Okay? Here's my table. Okay? And I'm going to put my test intervals here. So intervals. So I'm going to do 3 rows because x equals 2 is going to be my little guy right there. Okay? And we're going from negative infinity to 2, and we're going from 2 to infinity. Okay? All right. Let's do f of x. Let's do f prime of x. And let's do f double prime of x. And then let's do like characteristics over here. I made my table not long enough. Okay? Characteristics. Whatever that means. Okay? All right, now, usually we only plug this guy into the original. But we're not going to this time because he is a va, so he never actually has a coordinate point there. Okay? So, I'm not going to put anything there. He is a va, which means he is not a max, a min, or a POI. So he is not going to be anything. We're not going to have any maxes, mins, or POIs at all. So the whole reason why we do this table is just to figure out whether he's concave up or concave down, right? And where. Okay? All right, where are we going to choose between negative infinity and 2?
0.
0 and 3? 0 and 3, right? 0 and 3, 0 and 3. My first derivative was negative 1 over x minus 2 squared. And my second derivative was positive 2 over x minus 2 to the third power.
Why
Okay.
did you scribble those things out? I forgot.
Because we don't have anything here that we need to plug into the original equation. We don't have any like thing in that test interval that needs plugged into the original. It's this point exactly that we plug into the original. Okay, so we don't have to plug anything in there. Okay? Alright, here we go. If I plug 0 in here, negative 1 over negative 2 squared is going to be negative.
There's a monkey here.
Negative. Okay? If I plug 0 in here, 2 over negative 2 to the third power is going to be
Negative.
negative. Okay? So that means this interval is decreasing and
CD.
concave down. Okay? He's decreasing and he's concave down. Alright, now if I plug 3 into this top one, or the first derivative, 3 minus 2 is 1, 1 squared is 1, so I have negative 1 over 1, which is
Decreasing.
negative. Okay, if I plug 3 in here, 3 minus 2 is 1. 1 cubed is 1. 2 over 1 is positive. So this guy is still decreasing, but he is concave up. Okay, let's graph the function. We had something like, I said it probably is going to be a boomerangy thing, and he's going to do like something like this, right? And he's going to do something like this. Let's see if that matches up with our results, okay? In this first interval, which is this left one, we said that it is decreasing. Is that thing going down? Is it concave down? Yes. Okay, let's go to the other side. This one is the second interval that we have. We said he is decreasing. Yes? Is he concave up?
Yep.
Yes, so that is consistent with our results. This spot at 2 is neither a POI nor a max min nor an anything because he is a VOP. Got it?
Yes.
Yes, that's the first homework problem. Okay? Alright, the rest of it shouldn't be too bad.
What is all that?
Yeah, no.
It's literally 5 lessons. in one.
Okay, but
No.
Yeah.
there's nothing we can put in for those.
What? What you talking about?
Maximum.
And for what are you talking about?
I give up. Increasing interval.
What is all that? So like
Go-
the
go
increasing
over.
interval, there is none.
Go
No,
over.
there is. Oh, gotcha.
Going
I see
over.
what you're saying. Increasing interval, there is none. Decreasing interval, he is decreasing from negative
Oh.
infinity to 2 and from 2 to infinity. Okay? Maxes,
None.
none. Mins, none. Concave up from 2 to infinity. Concave down from negative infinity to 2. Points of inflection,
No.
none. There you go.
That's the weirdest thing.
There you go. There's all your stuff. Okay? Look at all that.
Did we-
Using derivatives.
Where's it
That's the worst thing I've ever seen.
The worst thing you've ever seen.
Papers?
Worst thing
Okay?
I've ever seen.
Good?
No, I'm not good.
No, you're not good? Alright, there you go. The backside one is is a lot better, I promise, because he doesn't have any vahs or ha's or anything like that. So, there you go. Okay.
Skip the extensions.
Skip the x-intercept because they're ugly, like we did on the notes. There you go. Okay?
If
All
there
right.
was no VA,
Goodbye, people watching the video.
Wait, we don't have to
Any
do
right
that
here.
first time?
No, on the back one, look at what it says.
Oh, wait, it does say skip. I didn't.
Can I have a paper?